I first became aware of Luke Harmon's work when I was getting a paper reviewed. I didn't actually know about it, but we had developed this new summary statistic on phylogenetics with timing information, actually with Tanya Stadler, who I think is in the audience here. And when we got the paper back, I said, why didn't you cite any of Luke Harmon's work? And indeed we should have, because he had developed, of course, some really cool likelihood-based approaches. And I'm glad that he's continued this work. And so he's going to present some of related work, it seems to me, today. And he is now an assistant professor at the University of Idaho with a quickly growing lab. All right, take it away. I'm going to disappear here.
Okay. Hi, everybody. Thanks for logging on to hear this seminar. I'm really happy to do this. I think it's sort of a glimpse of the future of science to do these online seminars. So I'm happily sitting in my office in Moscow, Idaho, where it's freezing cold and snowing, and yet I can talk to all you guys about what I think are some new frontiers for the comparative analysis of adaptive radiation. Before I go into some of the methods that we've developed in my lab that I'm going to tell you about today, I just want to tell you a story. And this is a story of a student of mine. We can leave him anonymous, but maybe it's more fun to give him a name. So let's just call him Travis. So this little stick figure right here is my student Travis. And one day, Travis was thinking about his research program, which involves adaptive radiation of geckos, and he came up with a hypothesis. And I have this hypothesis drawn in cartoon form here of a triangle leading to a star. So Travis has this hypothesis that maybe if we find yellow triangles, we can predict that they will evolve into green stars or something like that. So as we do in my lab, we like to incorporate field work and lab work. So here I've put a picture of a hypothetical field site for Travis. If you recognize this picture, this is actually Mordor from Lord of the Rings. And so I tell Travis that I think there might be some data for him in Mordor. So Travis goes out into the field to try to collect his data. And you can see him wandering around in the lava plains there. And so terrible things happen to Travis in the field, but he does manage to come back alive, and he's got his data. Now, this story is about comparative methods. So once you have your data, you need to analyze them. So Travis remembers his hypothesis. And I think typically the next step that people who do field biology and comparative methods might do is go look for some phylogenetic comparative methods. This is a heuristic picture of what phylogenetic comparative methods actually look like. Maybe you've never seen this before. This is a statistical comparative methods machine. I'm not going to explain this to you guys. It's got a lot of levers and pulleys and things like that. You can see the wires. But this is what it does. And I'm going to tell you about some other methods that are like this now. So this, you might look at this as Travis did and think this is kind of like my hypothesis. Not exactly, but close enough. So Travis takes his data, and he puts it into the comparative methods machine. Now here's where my lack of slide animations is going to fail. It's supposed to jiggle a little bit. And then it spits out a result. So Travis has actually taken his data and ran some comparative methods. He's very excited. Now he's got this nice green hexagon, and he brings it into my office. Here he is with his data. And I say, Travis, what is that? What does that green hexagon have to do with your hypothesis? And he says, I'm not sure. And that's kind of the end of the story. So what this is meant to illustrate is that we have data that we collect in the field. We have questions we want to answer, like triangle to green star. And then we have comparative methods that do things that are related to what we want to, the hypotheses we want to test, but they're not quite doing what we want in many cases. One of the goals that I have in my research program these days is to try to push comparative methods forward a little bit. And the way that I want to do that is to create methods that analyze the data that people actually have to estimate things that they really want to know. So instead of having to force your flattened little triangle into the comparative methods machine, let's see if we can build comparative methods that actually test the particular biological hypotheses that we're interested in. Now, when we're talking about the types of data that people actually have, often when people, myself in the past and other people imagine the kind of data that people are going to bring to comparative methods, they might imagine things like this. And if you don't know what this is an Anoles lizard right here. And this is a phylogenetic tree of anoles. Maybe you can't see it very well. It doesn't matter. And it has circles on the tips representing a trait like body size. So what we imagine when we're developing comparative methods is that people are going to bring their completely finished, fully resolved tree with perfectly accurate branch lengths, and they're going to have data for traits for every species in that phylogeny. I worked on Anoles a little bit in my PhD, so I know what that's like. It's really rewarding, but it's absolutely not typical for people to have data like that. Their data often have many different strange forms, and we should be developing comparative methods that work for the types of data that people actually have. What do people really want to know? Well, often comparative methods, people are trying to study processes like adaptive radiation. They want to know how ecology drives speciation and trait change. What are we providing for them in comparative methods right now? Well, a lot of comparative methods are based on a models like Brownian Motion. So Brownian Motion is, I'll talk more about this later, sort of abstract model for trait change. It's a random walk model. And even though this is a statistically easy to analyze model, and you can go quite far with that, I think this is not really what people want to know about. The connection between Brownian motion and adaptive radiation is weak or absent. And we can try to imagine circumstances where Brownian motion might be a good model to use, but they're not always the right circumstances. So that's sort of the background. That's my story of Travis and his comparative method adventures. And what I want to talk about today is how we're trying to work towards creating methods to analyze data that people actually have to estimate things that they really want to know. Now, this criticism that I just leveled at the entire field of comparative methods, I think you could totally still give this whole talk. So we're just trying to do this. We haven't accomplished it yet. I just want to give that caveat right now. But I do think that we're doing things that are going to help push us into the future of comparative methods, where we're going to analyze data that people actually have and fit biologically interesting models. So what I'm going to tell you guys about today are 3 different methods that have been developed in my lab group and some of our collaborators at UCLA. And so I'm going to go through these 3 different methods. One is called Fossa Medusa, one is called Htur, and one is called Meka. Now, before I go into these methods, you're going to see at the beginning of each little section a slide introducing the method, and that slide will have many co-authors, partially overlapping sets of co-authors for all 3 of these. And so what I mean to say by that is that this isn't really my work. It's the work of postdocs in my lab and in Mike Alfaro's lab at UCLA, and they should, I want to give them the credit that they deserve for helping me develop these methods. So the first method I'm going to talk about is called Fossa Medusa. And this method is being developed by a postdoc in my lab, Joseph Brown. Some of you might already be familiar with our method called Medusa. Medusa stands for Modeling Evolutionary Diversification Using Stepwise AIC. This was published by Mike Alfaro and other colleagues in PNAS in 2009. I should also give a shout out to Mike Alfaro for being the king of acronyms. Every single acronym in this talk is due to Mike. And also all 3 of them have an acronym within an acronym, which is sort of meta and cool. Anyway, so we have Medusa, this method. And what Medusa does is it helps us identify places on the phylogenetic tree where diversification rates have changed. And I'll go through that in a second. The extension that we're working on right now with Joseph Brown and these other co-authors listed here is called Fossa Medusa. And so you might be able to guess by the name that what Fossa Medusa does is it takes our Medusa approach and incorporates fossil information. Now, I think Medusa and Fossil Medusa and other similar approaches are really important right now. Recently, Dan Roboski published a paper showing that when clades vary in their diversification rates, so some have high speciation, some have low speciation, some have high extinction, others have low extinction, this can wreak havoc with current comparative methods. And in particular, Dan showed that variation in diversification rates across clades can misleadingly lead us to hypothesize high extinction rates in our phylogenies if we don't account for it. So what Medusa is trying to do is to actually account for this variation in rates of speciation, extinction, or both across phylogenetic trees. So what we're going to do, the big picture here, is that Medusa fits birth depth models to phylogenetic trees and fossil data, tests hypotheses about variation and diversification across these clades, and tries to find out if some clades are exceptional in terms of birth, death, or both. So let me just show you how Medusa works and then what's different about fossil Medusa. One of the key principles of the likelihood approach that we use in both Medusa and Fossa Medusa is Dan Roboski's idea of combining the likelihood equation for data sets like this. And what this is a phylogenetic tree. This is a really simple case. You can see that part of the phylogenetic tree is resolved here. And then we have 2 unresolved clades, this purple one and this orange one. So this is ties into what I was just talking about of analyzing the data that people actually have. What people have are typically not fully resolved trees, especially at higher taxonomic scales. They have incomplete trees where they have exemplar lineages, like they might have 1 species here that represents a whole genus of 40 or 50 species. So Roboski's insight in his paper in 2007 was that we can actually calculate a likelihood across this phylogenetic part of the data and a likelihood across these unresolved what he calls the taxonomic parts of the tree. So our total log likelihood is the product of the phylogenetic log likelihood, or the phylogenetic likelihood and the taxonomic likelihood. So what the Medusa method does is it takes that as a starting point. So here's a more complicated situation where we have 5 unresolved clades, a total of about 1,000 species in our group. The numbers on the right are the number of species in each unresolved clade. I've also colored them to so hot colors represent more species, cool colors represent fewer. So what Medusa does is it will fit models to this data. So we can fit a birth-death model, we can estimate parameters, get a log likelihood, and an AIC score. And then, so this is if speciation and extinction were constant across this tree. We can also break the tree on different branches and fit more complex models. So here we've broken the tree at this green branch, and we fit a 4-parameter model where we have one birth and death rate for this small clade up here with 8 species, and a different birth and death rate for this larger clade down here with 962 species. And then we can calculate a log likelihood and an AIC score. What you see from this calculation is that breaking the tree right here is not really a good idea. It actually increases our AIC score. But there are places on this tree where it's actually a good idea to break branches, such as this branch right here. If we make a break at this branch right here, we get a substantially lower AIC score. And what Medusa does is it steps through the tree, making one split at a time. So it goes from a 2 to a 4-parameter model, from a 4 to a 6-parameter model, and et cetera, to try to find to try to fit a complex model of diversification to our data set. So here's an example that we published in the Alfaro et al. Paper in 2009. This is a phylogeny of the jawed vertebrates. This goes from sharks to includes the fish and the tetrapods. Again, it's a heat map, so yellow is really species-rich groups, and the cool colors are really species-poor. If we run Medusa on this data set, we can identify 9 different places on the tree where we're justified in splitting the tree into different portions, where each portion has a unique speciation and extinction rate. So I'm not going to explain this anymore, other than you might notice that we have power to detect rate changes, and we can find places where net diversification has increased, the yellow boxes, and decreased, the blue boxes. But
Sorry,
what this
Luke,
is, yes.
Can I ask just a quick question? When you say the taxonomic part of the tree, can you just go back to that slide?
Yes.
The log likelihoods. Are you saying that when you say taxonomic, I think you're just saying unresolved, that
Yeah.
you're just sort of, so you have kind of the outside part of the tree, and then you have the part of the tree that's the big triangle, and that just says, I don't know what this is, but I think all of these things are together. And so how is that likelihood calculated?
I'm actually going to show you that in a second. We'll get to that.
Oh, okay. Sorry.
So that's a good question, though. So let's see. Let's just zoom in on one of these clades right here and talk about some of the details. And what I'm going to talk about is this clade Sphenodon, which are the 2 Htaras. So this is an example of our taxonomic data. We have an unresolved clade. This is kind of ridiculous to have this unresolved because there's only 2 species in it, but just humor me. It has an age of 250 million years and an extant diversity of 2 species. And then we know that its diversity at its origin was 1. So the data we're using for this, what I call the taxonomic part of the likelihood, is this time. So in 250 million years, we started with 1 species, and now we have 2. So the likelihood is the probability of obtaining 2 species given our time interval, our birth rate, and our death rate. Does that make sense, Frederick?
Yeah.
Okay. So what I want to imagine now is, and one of the issues with this type of method is that it doesn't use any information about fossils at all. And although theoretically we can say things about extinction without having fossil data, it makes sense to use the fossils that we have to try to inform us about extinction. And 2 Htaras are a good example because there used to be a lot more fossils than there are now. Here are the likelihood equations for this in case you're curious, but it seems useless to go over that. So 2 Htaras. This is made up, but kind of close to the truth. So let's imagine that 175 million years ago, we have a time slice through this phylogeny, and we know that there are 25 species of 2 Htaras alive at that time. And what we should include in this count of things are anything that would be in the monophyletic clade of organisms descended from this common ancestor here. So with this fossil information, we should imagine our diversity dynamics differently. And one way to draw that would be something like this. So now instead of going from 1 species to 2, we're going from 1 species to 25 species, and then back down to 2. So we can actually just change our likelihood equations to account for this fossil information quite easily by breaking our unresolved part of the tree into 2 parts, the first time of 75 million years and the second time of 175 million years, and calculate the joint probability of making these 2 observations over these 2 time intervals. And what that looks like is we can just do the first part, so the probability of going from 1 to our number of fossils over our first time interval, given birth and death, times the likelihood of our second section, the probability of going to N2, which is our number of extant species, starting with our number of fossils, given our second time interval, birth and death. Now, one issue with the fossil record that has been well discussed in the paleo literature is that the fossil record is incomplete. Some parts of it are more incomplete than others. And our estimate of the number of species that we have of tuataras today is pretty accurate. There are 2. I think if someone found a new species of tuatara, it would be really shocking. But finding a new fossil of tuatara would not be that shocking because of the incompleteness of the fossil record. So another thing we can do is to treat the number of fossils as a minimum and calculate the probability of going from 1 species to at least 25 over the first 75 million years, and then going from whatever that number is down to 2 species at the present day. And mathematically, this is easy because we can just calculate the probability of going through any number less than 25 and then take 1 minus that for the probability of going through any number greater than 25. Again, I'm skimming over details, and so people can email me if they want to know more about how the math works here. So the point of Fossa Medusa is we take our original Medusa approach and we can add fossil information from, say, a time slice that cuts through these unresolved taxonomic groups and see some diversification dynamics that were unobservable from our original molecular phylogenies. And then we can use that information to fit our likelihood models. I think this is a useful way forward because there's actually been some controversy about the evolutionary diversification of whales. I stole this picture off the internet this morning, and I'm quite proud of it. So the interesting thing about whales is that there have been a few studies looking at whale diversification using just phylogenetic information. But there's also a pretty good fossil record of whales, and also several groups of whales were more diverse in the past than they are now. There's a little bit of back and forth about this, about whether the tree is better or the fossils are better, and I think we can sort of sidestep that discussion by developing methods that use the tree and the fossils together. So we actually have applied this Fossa Medusa to a data set of the cetaceans. So here's a phylogeny of the whales. These little bars here are proportional to the number of extant species. So what I'm going to do now is I'm going to show you what happens when you run Medusa on this data set, and then I'll show you what happens when you run Fossa Medusa. So, and this data is from the paleobiology database. So if we run Medusa on the whales, it identifies one shift in diversification rates right here. And it contrasts this background rate of speciation and extinction with the rate in the Delphinidae, the oceanic dolphins. And what you can see with these likelihood surfaces, so these likelihood surfaces are surfaces for the net diversification rate R, which is birth minus death, and epsilon, which is death over birth. So high values are high extinction, 0 is no extinction. The red dots are the maximum likelihood estimates. And what you can see, even if you can't see this very well because of the slow internet and your small computer screen, is that both of our maximum likelihood estimates of extinction are 0. And this is something that we know for sure is wrong. There's been lots of extinction in whales. We can find species in the fossil record that just aren't around today. So this is an incorrect inference of 0 extinction. What happens if we put in the fossils? So here we've taken a time slice through our tree and found counted fossil species richness in all these different clades. And you can see those counts there on the slide if you can read that. So what happens if we incorporate this fossil information into our analysis? And here I'm treating the fossils as a minimum. What we see is now we have our base model, but we identify 2 different splits. First of all, we have high baseline extinction in the whales. There's been a lot of extinction in the background rates. We again find a shift in the oceanic dolphins here, and this likelihood surface isn't different from the one that you saw before because there are no fossils incorporated in this part of the analysis. We also identify a second shift in diversification rates in this clade, the Baleonopteroideae. And so Fossa Medusa gives us 2 things here that were different from original Medusa. We can estimate levels of extinction that are non-zero, which we know is correct for whales, and we can also have the power to resolve additional places in the tree where speciation and extinction rates have changed. So here's just a plot of the background rates from the analysis with no fossils. This is the likelihood surface of, again, R versus epsilon for no fossils versus with fossils. And you see that the likelihood surface changes dramatically when we incorporate fossil information.
So is it possible to get a non-zero extinction rate without the fossils?
It is, actually. It's pretty common to get high turnover models without fossils. So both in theory, it's possible to do that, and in practice, people have found that result as well. It's a little bit difficult to interpret because of Rybowski's finding that we can confuse rate variation with high extinction. But nonetheless, you can estimate extinction without fossils, and it's based on this phenomenon called the pull of the recent that I'm not going to go into now, but that one could Google. So what we're working on with extensions of Fossa Medusa, what Joseph is working on, when I say we, I mean Joseph, is he's making it much, much faster. For those of you with experience with Medusa that I wrote, you might have this idea that Medusa doesn't work. Yes, I hear you. I'm sorry for that. Joseph's version does work, and it's actually documented, and the code has comments in it. And he's working on multi-core support. It should be able to handle hundreds of thousands of tips. We're extending it to consider multiple observations of fossil richness along a single edge. He's putting in a way to test specific hypotheses of rate change, extending it to consider a distribution of trees. Lots of different extensions are going. The other thing that's happening with Medusa right now that's worth mentioning is that in the original Alfaro et al. Paper, we suggest a cutoff of AIC values of 4 is a good idea to choose splits on the tree. What we're finding with some simulations analyses is that value of what AIC cutoff to use depends on the size of your tree. And you should use higher cutoffs with bigger data sets. So we're trying to quantify that now and describe it in detail. And here's just an example. This is all in R, so I'm not going to go through this, but just so that you know, it exists in R. We're gonna put it into Geiger 2.0, which should be coming out this summer. And so you'll be able to run this on your data easily and quickly. So that's Fossa Medusa. Again, Joseph Brown, postdoc in my lab. And if anyone is hiring anyone in their department, they should try to hire all the people that I'm going to talk about today immediately. The next method that I want to talk about is a method that's called Htur. This is the work of John Eastman, who's a postdoc in my lab. Htur stands for Accommodating Uncertainty in Trait Evolution using R. And here's the co-authors on the Htur project, including Mike Alfaro, Paul Joyce, Andrew Hipp, and myself. What we're asking with Htur is whether the rate of trait evolution varies across clades in a phylogenetic tree. So this is similar to Medusa, where we're trying to find variation across clades in a tree. But now instead of talking about speciation and extinction, we're talking about rates of trait evolution. And in particular, what we want to know is, are traits in some clades evolving faster than in others? So here's an example of the type of data set that you might want to analyze with a method like Htur. This is going back again to Anoles. This is a phylogeny from Luke Mahler and his collaborators, published this last year in 2010. And what you see is that there are different species of Anoles. They live on different islands in the Greater Antilles, Cuba, Puerto Rico, Jamaica, and Hispaniola. And we might wonder whether the rate of trait evolution varies across those different islands. Now, there are methods that are out there that carry out these kind of methods. And I think the best example of that is an approach called Brownie that was developed by Brian O'Meara, who's giving the next phyloseminar. The difference between what Htur does and what Brownie does is that Htur doesn't require any a priori hypotheses about places on the tree where rates might be changing. Htur is, in this sense, more exploratory. You can just give it your data, and it will search for places in the tree to put changes in the rate of evolution. So Htur can identify clades with distinct rates of traits evolution in the absence of any prior hypotheses. I think this is a useful approach, and I think it's useful even in the context of data sets where you do have prior hypotheses, because you can write those hypotheses down and then run Htur and see if it finds the same places on the tree that you would have identified as interesting beforehand. Okay, so how does Htur work? Something's happening. Well, we're going to assume the data that nobody has, which is what I criticized at the beginning. I'm also going to use Brownian Motion, so I'm just going to contradict everything that I said at the beginning of this talk, but I think you'll see where this is going. So we're going to assume that you have a phylogenetic tree, and you have a bunch of data for continuous traits. Htur right now only works for continuous traits. So you might have species means for something like body size. The way that Htur works to fit these complex models of rate evolution is using reversible jump MCMC. We can abbreviate that as RJMCMC. So for those of you that haven't heard of reversible jump MCMC before, I'm going to give you a really brief heuristic look at how it works. But reversible jump MCMC is a Bayesian Markov chain Monte Carlo algorithm that can jump between models of differing complexity. And what we mean really by different complexity is just different numbers of parameters. So when we're doing our reversible jump MCMC, we're running a Markov chain Monte Carlo analysis. We have generations. Each generation, things are changing about our model. And we should, after an infinite amount of time, converge on the posterior probability distribution for all of our parameters. So in the reversible jump MCMC, during this MCMC walk, we have three different things that can happen. We can update our parameter values, like the root state for the tree, and our rate category is sigma squared. That's just like normal MCMC. But we can also do two new types of moves that are called splits, where we split a single rate category into two, and merge, where we merge two rate categories into one. Let me show you how that works. Here's an example of an abstract model that has a single parameter, alpha, and I'm denoting that it's alpha 1. And we can sort of partition that up. Maybe these are different branches in the tree. Maybe this is the rate of evolution. So here, all the rates of evolution are the same on every branch of the tree. In reversible jump, we could update this parameter value and choose the different values of the parameter. But we can also do splits, where we split from a single parameter model into a two parameter model, alpha 1 and alpha 2. And so you can see that some of our alpha 1s have stayed the same. Others have changed to alpha 2s. Now we have two parameters. We can do another split and add a third rate category of alpha 3. And then we can do a merge and merge our alpha 2 and our alpha 1 back into a single category and go back down to two parameters. So this is just sort of a heuristic description of what's happening when you do reversible jump MCMC and how you can move around in parameter space. So in standard Bayesian MCMC, we calculate our acceptance probability by multiplying the prior odds by the likelihood ratio. The difference in reversible jump MCMC is that we can also do split or merge moves, and when we do split or merge moves, we add this additional factor called the Hastings Ratio. And I'm not going to tell you what the Hastings Ratio is. You can look it up in other reversible jump MCMC papers, like a paper by Hulsenbeck and colleagues from a few years ago. But basically, it corrects for what happens when you change the dimensionality of your parameter space. It penalizes or promotes that sort of thing. So we're just adding this. We take our standard Bayesian MCMC, add on split and merge moves, correct for them using Hastings ratios, and now we can get posterior probability distributions across multiple models, each with different numbers of parameters. So let me give you an example that John Eastman has run, and this is a really cool example because it has such an interesting and clean result. And so what John Eastman has done, and this is a massive amount of work, is to go through hundreds of species of salamanders around the world, use GIS approaches to calculate how fragmented their ranges are. And so you can see his data here. These are sort of the centers of the ranges of lots of salamander species. You can see there's a lot in the southeastern US and in Central America, and then calculated how fragmented their ranges are. So species with highly fragmented ranges like this are big circles, and species whose ranges aren't fragmented at all are small circles. He's then used Htur to fit multi-rate models of the evolution of fragmentation to the tree of salamanders. So what this is looking at is how fast do species of salamanders change their level of fragmentation. So if they stay fragmented or not fragmented for a long time, that's a low rate. If they oscillate back and forth quickly, that's a high rate. So you can see that you get these likelihood traces. This looks weird if you're used to looking at normal MCMC likelihood traces, but it's pretty typical for a reversible jump that the merge and split moves cause jumps in the likelihood. These are two different runs. The black one is one run and the gray one is another. And so you can see that the two runs converge on more or less the same posterior distribution of likelihoods, although they're jumping at different frequencies. Here's our prior. So we put a prior distribution on the number of rate categories here that favors simple models over more complex models. And you can see our posterior distribution, which has shifted considerably from the prior distribution. The prior distribution is gray, posterior is black. And you can see there's very little probability weight on the prior distribution for 3 rate categories, but a substantial weight of around 0.5 in the posterior distribution. And we have weights spread out on some higher numbers of differences in rate categories as well. So what this means is if you're in this category 3 here, it means that we have 3 different rates of range fragmentation evolution on the tree of salamanders. We can also do things like this. So this is a plot that where the branches are colored by their rate of range fragmentation evolution. Cool colors are slow and warm colors are fast. And what you see is that there's a massive increase in the rate of evolution of range fragmentation in one clade of salamanders, the Bolitoglossinae. These are really cool salamanders. They're lungless. They, unlike many salamanders, tend to live in the tropics. Some of them are projectile feeders, which is cool. So this really interesting and cool group of salamanders that has quite a different life history pattern, and also is very species rich, has an incredibly fast rate of change in range fragmentation related to its relatives. And I think that this is related to what we think about as important in driving diversification. And so the other thing you can do with Htur that's cool is you can calculate rate averaged estimates or model averaged estimates of evolutionary rates. So what this is two probability densities. The gray one is for the background of all salamanders, and the red is Bolitoglossinae. And these are averaged across the uncertainty that we have in the number of shifts that Htur is putting on our tree. And you can see that even given that uncertainty, we can say with really good confidence that the rate of range fragmentation evolution in salamanders is higher than the background in the Bolitoglossinae. So again, this is our Htur method. This is developed by John Eastman. This paper is in review right now at Evolution. The last method that I want to talk about is a method called Meka. This is a method that's been developed by Graham Slater, who's a postdoc in Mike Alfaro's lab at UCLA. So Meka stands for Modeling the Evolution of Continuous Characters Using ABC. You can see the authors there. I'm really proud of this logo from Meka. I think it looks awesome, but I gotta just fess up to the fact that I didn't make it up. I stole it off the internet. Turns out there's a clothing company called Mecca Clothes that makes that, and this is their logo. I like it. What I also like is I've already created a T-shirt that I want to suggest is the official T-shirt of Mecca. Here it is. If you can't read it, it says "Get Money University," and you can see the little Mecca logo there. You may not be able to tell that I used Photoshop to do this, but I did. I haven't been able to purchase this shirt for myself yet, but I will. I see a question actually from Raphael about.
Oh, I'm sorry. I was helping someone with a technical issue, and they were personally chatting me. Yeah. Well, go ahead. You can read. Would you mind reading off the question, because
yes.
That's
So
not
the question says, how big in terms of terminal taxa or nodes must a tree be in order for this method to work or be stable? I think this question is about Htur, and we've done a set of simulations showing how much data you actually need to have reliable estimates of rate shifts on trees. The trees, if your tree is of reasonable size by current comparative method standards, say 40 taxa, then it should be big enough to detect rate increases or decreases I mean, it depends on how big the rate increase is. You need bigger trees for more subtle changes. But our simulations have shown that for rate shifts on the order of what people have observed in the natural world, a tree of 40 species is big enough to detect that. And Raphael, if you want to post follow-up on there, go ahead. But I will just press ahead. So Meka is another method for dealing with these unresolved data sets. But now we're going to try to work in both speciation and extinction and patterns of trait evolution. So what we're imagining here for the Meka data set is imagine you have this unresolved phylogeny, you have these terminal taxa, and you don't know the relationships within those clades. But you might also have some really reliable information for traits in those clades. And you can get this information without measuring every single species in that clade. So what we're going to imagine here is that you have an estimate of the mean for some trait in that clade. Here we have body masses. And then you have an estimate of the variance of that trait in that clade. And I think you can get a good estimate of the variance if your traits are more or less normally distributed from like 20 species. So even in this 950 species clade, you don't have to measure everything. You just need to know the mean and the variance. And what Meka is going to try to do is to use these types of data to address questions in comparative methods. Now, we're going to add something on to MCMC again. So going back to our standard Bayesian MCMC, to make our steps in the Markov chain Monte Carlo, we need to know the prior odds and the likelihood ratio, and then we can calculate our acceptance probability. Here's a nice slide that Graham Slater made that sort of shows how this works. So we have our prior distribution here for some parameter theta. We can draw from that prior. We can compute the likelihood of the data under our model M with our parameter that we've drawn from the prior, theta prime. We can calculate our likelihood ratio, and we can use that likelihood ratio to decide whether we want to accept the proposal with some probability. And so in this case, we have accepted it, or in other cases, we might reject our draw from the prior. And after many, many steps of this Bayesian rejection method, we converge on our posterior distribution of parameter estimates. But likelihood ratio is actually kind of the mathematically hard part of this series. And you might wonder what we can do if we can't compute the likelihood ratio. Well, up until a few years ago, then if you can't compute the likelihood ratio, then you basically can't do Bayesian MCMC searches. So what this means in terms of actual models of evolution is if you can't analytically solve your model and produce a formula for the entire distribution of outcomes of that model, then you can't fit it to data very easily. But that obstacle has been overcome by a relatively new statistical method called Approximate Bayesian Computation, or ABC. This is becoming more and more common in biology. I see it popping up a lot especially in population genetics. And I think this method has a lot of promise for comparative methods. So here's another nice set of slides that Graham made that show how ABC works. So again, we're going to draw from our prior. But instead of calculating a likelihood, we're just going to simulate data under our model M with this parameter value, theta prime, that we've drawn from our prior. And then we're going to shoot that simulation at a target. The target here is our actual parameter or summary statistics for our data. That's what this little black dot represents, is some set of summary statistics that describe our data. And then the red dot is the summary statistics that we get out from our simulation. And you can see in this picture that this red dot is kind of far away from the black dot. And in particular, it's not inside this little circle right here, which math dorks like to call E-ball. And so because it's not inside that circle, it's not close to the target, we throw it out. We draw again from the prior, shoot at the target. Now we've hit pretty close to our data. What that means is that if we look at our simulation and calculate a set of summary statistics, those summary statistics are similar to the summary statistics we have in our actual data, then we keep that draw from the prior. And the nice thing about this is that even without likelihoods, we're still able to converge on the posterior distribution of our parameter. Now, this is really, really computationally wasteful. So you need many, many simulations per generation of your Bayesian run to converge on your posterior. Basically, for us right now doing this stuff, here we have to use our cluster and have a lot of computational power to make it work, and it still takes a long time. So let's get more specific and talk about how we're actually simulating our data in Mecca. Again, this is the part where we draw from the prior, we simulate data, and then we're going to shoot that at the target of our data. So we have our phylogeny with our unresolved clades. We draw an ancestral character state, theta, that's the starting value for, let's think about body size. We simulate characters along every branch in the tree under a Brownian Motion model. But then we get into these unresolved clades, and that's where something interesting has to happen. So when we get to these unresolved clades, we simulate our characters using what's called the branching diffusion process. And the way to think about that is basically it's birth-death plus Brownian motion. So we grow a birth-death tree, and then on that birth-death tree, we simulate our characters under Brownian motion. So draw an ancestral character, simulate characters along the branches, and then do branching diffusion within our unresolved clades. In terms of our summary statistics, what we're going to use is, for every clade, the mean trait value across species in that clade and its variance. So when I was talking about that little target, our target here is actually the variance of each clade and the mean. And we want to find sets of parameters that give us means and variances across clades that are close to what we see in our data. This is an oversimplified version because this is imagining that you just have one mean and one variance. If you have n clades in your tree that are unresolved, you're going to have n means and n variances. So you're going to have 2n different summary statistics. And so we're going to calculate the distance between the data and the simulations in that 2n dimensional space. So what we do then is we have our phylogeny, and we can draw parameter values out. So we can draw from the prior a birth rate, a death rate, simulate our unresolved clades, draw an ancestral state and a rate of evolution, see whether the means and variances we get of those clades are close to the target value from our data, and decide whether to accept or reject those parameter estimates based on those distances. And at the end, we get a posterior distribution for all 4 of our parameters. Now, this works pretty good, but we're still in this sort of birth-death Brownian motion world. But the great thing about ABC is that all you have to be able to do is run simulations. If you can simulate the process, then you can fit it using ABC. So one simple extension to Meka is to do something similar to what we were talking about in Htur or Brian O'Meara's Brownie. We can have a multiple rate model where we have speciation, extinction, an ancestral character state, and then 2 rates, 1 rate for the blue clades and 1 rate for the green clades. We can draw from our prior, we can simulate our data, we can compare the summary statistics from simulations to data, calculate distances, and again, converge on our posterior distribution. Now, I think that this type of method right now has the best chance of helping us break free of the constraints of current comparative methods. We already know that birth-death is not that great of a model for growing trees, but we don't have very many alternatives. We already know that Brownian motion is kind of crappy for a lot of data sets, but the great thing about ABC is that if you can simulate it, you can fit it. So no matter how complicated the model is, as long as you can simulate it efficiently, we can estimate parameters, get posterior distributions, and even do model comparisons. So we've applied this Meka approach to a data set on carnivores, and I'm going to talk about testing a 2-rate model comparing the rate of evolution of all carnivores to this clade here that's in the box. That's the pinnipeds. These are the aquatic carnivores, basically. And so we can use ABC to actually fit 2 different models. M1, a common rates model where there's just 4 parameters, birth, death, an ancestral state, and a rate for Brownian motion, versus a distinct rates model where carnivores, background carnivores have a different rate of body size evolution than the pinnipeds. And this is a reasonable hypothesis to test because you might think that when mammals go in the water, they can become bigger. So when we run this through Meka, we get posterior distributions. These are not the raw posterior distributions that come out of Meka. We've actually used a trick here developed by collaborator Daniel Wegman that allows us to smooth out these posterior distributions using generalized least squares. But I'm not going to talk about that now, so if you want to know about that, just ask me later. But you see we get these nice probability density distributions for speciation and extinction, lambda and mu, across the carnivores. But we're also not just, and so we get point estimates and confidence limits for those parameter values. Those confidence limits are pretty big, but it's hard to estimate speciation and extinction rates from phylogenies.
There's a question here. I will turn their mic back on. You might have heard them kind of talking in the background. Are you there?
Jose.
Jose?
What's up?
Jose, are you there?
Yeah, I can hear you. Go for it. Right now, it's univariate. We're just using one, it just deals with one trait at a time. And so there's just 4 parameters for the basic Meka model: birth, death, ancestral state, and variance. One could, I think, pretty easily do this for more than one trait at once. And so you can do like multivariate Brownian motion models for, with that trait variances and covariances. We haven't done anything with that at all, so I haven't even tried that, but I think it would be possible. So for model 1, where we assume that we just had a single rate of evolutionary change across the whole tree of carnivores, we can see that we can estimate that rate quite well, actually. Here's the posterior distribution. And we can also get a pretty terrible estimate of the ancestral body size of all carnivores. And that's typical of ancestral character estimation in general, and it applies to this case as well. And so we get our estimates for how fast body size is evolving in the carnivores and how big the ancestral carnivore was, which is somewhere between 1 and 32 kilograms. It's probably in there somewhere, yeah. Things get more interesting if we look at model 2 and compare the rate of evolution of the background carnivores, denoted by the howling wolf here, and the pinnipeds, denoted by that sea lion. And you can see maybe a little hint that the pinnipeds might be evolving more quickly than their background rate, but you can see it's quite uncertain as well. But if you look at the confidence limits for those rate estimates, you can see that they're pretty broadly overlapping. So we actually don't have any evidence that body size is evolving any more quickly in the pinnipeds than in the rest of the carnivores. We can even do things like Bayes factors. To get from an ABC algorithm to a Bayes factor is complicated, and I'm not going to talk about how that works, but I'd be glad to tell anyone about it afterwards. The point of this just is that we can get marginal densities of our two models and compare them directly using Bayes factors. And that, again, gives us back the same result that we don't have any evidence that for model 2, it's better to just pick model 1 where there's a common rate across all carnivores. It's not saying that rates haven't varied across carnivores, just that we can't detect it at this particular node that we've chosen to test in Mecca. Now, the way this talk is set up, you might be thinking about combinations of the methods that I've talked about. So using ABC in this reversible jump framework, all those things I think are possible. These are like puzzle pieces that we can put together in different ways when we're trying to figure out what to do with comparative methods in the future. So again, this is Mecca, and this is Graham Slater's work. All those really nice slides of the trash cans and the posterior distributions are due to Graham. So I think that if we go back to the goal of this talk, to create methods to analyze data that people actually have to estimate things that they really want to know, honestly, I've failed to do that. But what I think is useful about the 3 methods that I've talked about today, Fossa Medusa, Htur, and Meka, is that they provide tools that I think will help us do this in the future. And the types of data that people actually have are data that are uncertain in many different ways. And the way I've talked about today is unresolved terminal clades, and are also diverse. So people don't just have one type of data, they often have many types of data that they like to combine together in a single analysis. Fossils and trees are a good example of that. In terms of estimating things that people really want to know, I think that it'd be useful to push these things towards more biologically realistic models. Take models from quantitative genetics, or try to translate Simpson into math, and test those models using these types of approaches. So before I open it up to questions, I want to thank the Roha Lab, which is our lab group here at the University of Idaho with Erica Rosenblum, and the Alfaro Lab at UCLA. I want to thank NSF, NIH, IBEST, and Beacon for funding. And then there's about 1 billion people in that little tiny list right there that are all people that have contributed to these 3 projects in many ways. And then there are also lots of people that I forgot by accident. So thank you to those people as well.